fair warning, you are being recorded right now. Okay.
Awesome.
Just something that you'll notice while I record. The microphone is over there, so a lot of times when I'm recording class, you'll find that I talk louder than I normally do because I'm trying to make sure the microphone picks me up. So that's if it appears that I'm shouting, I am.
Is that as far as the wire really?
Yeah, that's as far as wire goes. It's not the best microphone in the world. So there are better microphones for doing this, but that's what. Sam?
Like I was on there, you couldn't. Sure.
Yeah, sometimes it's not. Yeah, sometimes it doesn't sound so good. But if there's this going on, that will definitely like.
Mr. Plans, do you want to use highlight? I have like a studio microphone.
Do you have it with you? Okay, well then I can't use it.
Not really helpful.
Carry the studio.
All right.
Of course you can.
It's just the microphone I have. Now, I'm not saying it's not saying it's a microphone I want to use. It's just the only one I have right now. So, all right. Yesterday, our discussion of quantum numbers, orbitals, sublevels. What we're trying to do there is there are certain areas around the nucleus where we're more likely to find electrons than other areas around the nucleus. Okay? Hallie asks, how come? Somebody want to tell me? Why are there certain areas around the nucleus where we're more likely to find electrons than other areas? Okay? Josh, go ahead.
It's because, like, they opposites or like they repulse each other.
Okay. What repels each other? The electrons themselves. But there's something else that enters into that factor. Yeah. The nucleus and the positive attraction. So Hallie, what we're finding there is that there's these two forces that are acting on these electrons. There's an attractive force from the nucleus because the nucleus has the positive charge, the electrons are negatively charged, so they're attracted to the nucleus. But now there's a bunch of other negatively charged particles, the other electrons, that are all repelling that electron.
It just happens to be like where they go.
Right. That's where they.
Balance.
Right. That's where they settle in.
This is where they settle.
Yes, basically. How you said it nicely. The balance between the pull from the nucleus and the repulsion from the other electrons.
So it's like an equilibrium.
Yeah, pretty much. Although technically equilibrium means that we're staying still, and those electrons aren't really staying still.
Well,
but yeah, it's the idea. The idea is yes. Okay. Carter, go ahead.
So is like the energy from that repulsion enough to make it change from like n equals 2 to n equals 3?
No, that energy has to come from some outside source. Like we talked about here with these lights, that energy comes from the electricity that comes in from the wall. Electrons won't necessarily jump up on their own. They have to jump up because of some increase in energy, but they have to give it from somewhere else. Okay?
Just like when you're on zaps, when you're like passed out or something with your things, and you jump up because they put electricity into you.
Yeah, it's similar to that. It is positive, it is energy, so it's the ability to do stuff. In that case, it makes your muscles contract. In this case, it makes electrons jump from this orbital to this orbital. Okay? Missy, go ahead.
It's kind of just like a clarification question.
Okay.
But you know how in like the L1,
Yep.
There's those like the bumps on the outside,
Yeah.
the N2 or whatever.
Yeah.
So are those just because they can't fit into the circle?
Pretty
they
much.
just go like fit them equal so that they're close enough at 5.
Right, exactly. And also, Missy, that's actually why when we look at, let's see if I saved that picture. Okay. When we start seeing these bumps, which this is what you were kind of referring to, right?
Yeah.
Okay. When we start seeing these bumps, we start seeing first they appear like along the x-axis, but they also start appearing along the y-axis because if you got two electrons and you're trying to keep them as far apart as you can, this is your option number 1. Okay? Hi. Check across the hall in the science office. Your first option is this, because that's as far apart as you can get them, right? Okay? Your second option, so you got these two here. If you're going to add a couple more, right? Because now 90 degrees between each of them. And then a third option is this one. So it's not a coincidence that they start showing up along the x-axis, the y-axis, and the z-axis, if you have a bunch of particles that are repelling each other, you can't get them any farther apart than that. Does that make sense?
Yeah.
Okay.
Well, why would it be a x-axis, y-axis? Because an electron is not a 2D figure.
Right.
It's
Kelly, this is it. Yeah, there is a third dimension that's coming out like this. Yeah, it's an XYZ. It's a, Kelly, I'm trying to represent a three-dimensional idea in a two-dimensional board.
Can we see this on real life?
You have to construct it yourself.
Yeah, kind of, yeah. So, they're like, you can't see the atom, right?
Then how people tell?
Well, Kelly, that gets back to like this, that when we start putting these locations, okay, we can identify, we went through this yesterday, so. But actually we were using you as an example in this
I
class.
heard.
So, but anyway, when we start using, I can't remember who we were using in third period, I don't remember, but anyway. We can find out where an electron was at a certain moment in time.
How?
It deals with the amount of energy that it gives off, like when it jumps up and falls back down. We can kind of tell where it was and where it ended up. Okay, you don't have to worry about that necessarily, but all of these dots on this picture represent the location of an electron at a particular moment in time. When we start stacking, like we take a picture now, and a picture now, and a picture now, and a picture now. And when I say a picture, it's not like a camera, all right? It's a set of calculations, and then, that comes out to that fixed that location. But when we take all those pictures and start stacking them on top of one another, we find out that there are certain areas where there's more dots. And that's what we're really talking about here, Callie. Those dots, those areas of a lot of dots, that represents areas where we're most likely to find electrons. Why? Because they've been there in the past.
There's just like their energies there.
Right, right.
But you said the electron's not there. The energy's there.
Now the electron could be there, and most likely it is, but and that's why we say that it's a most probable, right?
Just detecting the energy rather than actually seeing it.
Well, the energy
Well,
part.
that's something like Flickr, though. Like they're detecting the energy.
Right, yeah. And then because of that, the energy part is more the explanation for why those certain areas exist. So the energy part is more of like theory explanation for, okay, why are these the areas instead of those the areas? Okay? Josh, go ahead.
So, on the figure 8-ish sort of thing, the electrons on the side are pushing, like each electron is having two other electrons push on it from the side.
Yeah, basically, yeah. Although it's not necessarily just two other electrons. Even though, so like if this is the p orbital that we're talking about, right? It feels a repulsion from this electron, but it also feels a repulsion from this one, and this one, and this one, and this one. And all of those ones that are in the s orbital of the first energy level, it feels repulsion from all of them. Plus that pull from the nucleus, that's like right there, and that's just where it settles because of that. Okay, Missy, go ahead.
Can you go back to the picture? Okay. Wait, go two more. Yeah, that one.
Okay.
Okay. So, for each of the little bumps on the side,
Yes.
Is there two electrons in each of those, or is there just one?
This is more, well,
I think the bumps just the.
Missy, those two bumps actually represent like this whole orbital. Does that make sense?
Yeah.
Okay. So technically, there's two electrons within that space. Now,
But, so one bump is just one figure 8.
it's one side of the figure 8. Yeah. This figure 8 represents this part plus this part.
Yeah.
Okay.
So there's like one on each side, but didn't we say that technically since there was two, like what we did yesterday,
Yeah.
since the one had two electrons,
Right.
and on each side there's technically 4.
No. This plus this represent the entire figure, are represented by the entire figure 8. And two electrons exist within that figure 8.
So there's only 2.
There's only two.
So like if it was like equal, you could say there's one in each of them.
Yeah, I guess you could kind of think of it that way, and that's fine. If you think about it that way for now, that's perfectly fine. Okay? Kevin, go ahead.
It's just a clarification on the variables and LMS
Okay.
thing. So the N refers to the S orbital,
No.
or like that's like the circle bit, right?
The N refers to the principal energy level, which is like the big.
I thought you
the big
called that the S orbital.
no.
Not what it is.
No.
Okay, so that refers to the principal energy level,
Right.
which is like the
That's like
circle that it's on, right?
this circle that it's on.
Right,
Like,
so
is it on this circle or this circle or this circle?
Okay, so then L refers to the P orbital.
L refers
So
to
the figure eight.
is it in an S orbital or a P orbital within that big energy level?
So S orbitals are being on a circle, and P orbitals are being on the figure eight type deal.
Right, but that L value, this value, tells you, is it in an S orbital, or is it in a P orbital, or is it in a D orbital?
So if it's,
What's that?
wait, what's a D orbital?
Isn't that like weird
Like
blue
the
one?
next
That weird blue
Come
one
on.
that looks like something.
Like that one?
Oh,
Yeah.
all right.
Oh,
So
the
if it's
S
like
is the
L,
sphere.
so
And then the P is the dumbbell. Why? Or the square figure.
right. So
So that L value tells you, am I in an S orbital, or a P orbital, or a D orbital within that principal energy level?
okay, so N is which level it's on, and then L is which orbital it's on. N is
M,
which one of those orbitals?
right. And P, there's 3 P orbitals there are. So you gotta tell me which one. And then, yeah, S, you could think of as which side of that orbital
So
is
wait,
it.
would M only apply to a P orbital?
No, it also applies to a D orbital because it applies to any kind of orbital that there's more than one type. Okay? S orbitals,
So
there's only one kind of S orbital in each level. There's 3 kinds of P orbitals in each level after 1. There's 5 kinds of D orbitals in each level starting at 3. Well, yes, this is, I posted this all online yesterday. Yeah, all the writing and everything. Alright, Josh, go ahead.
On the homework, number 32 and number 33. Number 32 says how many different orientations are there for the P sublevel.
Yep.
And number 33 says how many orbital shapes exist within the second energy level.
Yeah.
Would those be the same question?
No. Okay. So, Josh, take these questions, okay? Well, actually, the 31, 32, and 33 are actually pretty good questions, okay? So when it says 31, it says how many different orientations are there for the D sublevel? What that's asking you is how many different kinds of D orbitals are there? And how many different kinds of D orbitals are there? 5. No, D orbitals are like the...
The weird like.
The weird thingies.
it's like
SpongeBob.
it's like the axis
Sure.
spoke thing.
You can look at... Actually, they're kind of more Patrick,
Yeah.
but
Oh,
Patrick,
yeah.
but Patrick has 5 because he's starfish.
Yeah.
You know, stuff.
So, Josh, how many different orientations are there for the P sublevel? So that's how many different kinds of P orbitals are there?
Four.
3.
How's it done though? Because of the
Oh, the X, Y,
X-axis, Y-axis, C-axis.
Is the P the only one with 3 different
Yep.
types? Why?
And then that's because, Hallie, when we get to the P level, we're just a little bit farther out. The S level is only spherical because it's the closest to the nucleus, and that's how it orients itself. But when we start getting to the P sublevel, that's when it starts going like this, and like this, and like
But that's more
this.
space.
That's more space, spread out. And then the D's, they spread out even more because it has more space, because it's outside of the P level. Okay?
So there's even more.
Right. And then F, which we just talked about in
So-
class, there's even more possibilities.
These only happen for elements
Like
in the
if
water.
if like the D orbital broke, what would happen?
Hold on 1 second.
These only happen for elements in the water.
Unlikely, but not impossible.
That's when we get to D's and F's.
Okay, then why is it elements? So what element?
Well, right now we're just talking about it generally.
I don't know.
And then, so Josh, for 33, when it says how many orbital shapes exist within the second energy level, So we said that each energy level has an S sublevel, right?
Right.
So when we get to the second one, we add which sublevel? Nope.
Or, sorry.
P next. Then when we get to the third level, that's when we start adding the D's. So because we're in n equals 2, there's only 2 sublevels. There's s orbitals and there's p orbitals. So there aren't any D's in that second level.
And then I'm going to ask, like, what is the total number of orbitals in the second energy level? That would be 4.
Yes. Julia, go ahead.
Can I see your N2 notes? N2. No. Wait, like, how do the electrons travel? Do they like
Okay.
go in the
Oh,
eight?
that's no. Actually, that's a good question. That relates to something that Haas asked. Okay. Now.
Yeah.
Okay. Haas asked before. He goes, "What happens if like a d orbital breaks?" Okay. Now.
How would it break?
What? No. So, don't think of this. This is not a confined area.
No.
It's not like a fence around a yard. Okay, right. It's not saying you can't go outside of it. And Julia, it's not saying that this electron just travels along the edge like this.
How does it
Okay?
travel?
It travels sort of in a random fashion anywhere within that area. This is like your yard that doesn't have a fence around it. Okay? Where does your yard actually end?
Nowhere.
Kind of hard to say where you're like. Yeah, well, but see, if you like say like my neighbors on either side of me,
They both have fence.
right? None of us have fences in our front yard. So when we're cutting the grass, you kind of have to like, okay, like I'm gonna cut like to about here-ish. Like you have to decide where do you stop cutting the grass. Does that make sense? It could be nice, and sometimes my neighbors are nice. And the one guy next to me, he just got a riding mower, so he cuts a lot more now because he's like it's on his riding mower, so he cuts like a lot more into like my yard.
Oh.
But like I said, it's not like a defined area. So Haas, this orbital can't break because it's not really like a confined space. It doesn't have a boundary to it. It's just an area that we sort of say, okay, this is where we're most likely to find this electron. Is it possible that every once in a while you go over into your neighbor's side of the lawn? Yeah, it is possible. Does that mean you aren't in this orbital anymore? No, you're still in that orbital. And Julia, just because you're not on the sidewalk of your yard, right, you're in the front yard,
You can be in the grass.
this electron still has this exact same set of quantum numbers if it's here or here. Does that make sense?
Yeah, and like, what if like most of them were on one side and it were like sent it towards the nucleus? Could it like stick onto the nucleus? Is it possible?
It is possible, but think about it this way. Julia. First, remember that the nucleus is the size of a marble in a football stadium.
Yeah.
Right? And the electron itself is 1/2000th the size of the marble. You know what I'm saying? So our odds of that electron actually hitting the nucleus is pretty small.
Okay.
Also, in order for it to actually get to the nucleus, it has to go through the S sublevel of the first if we're talking about the second energy level, it has to go through the S sublevel of the first energy level, which also repels it, right? So the chances of it running into the nucleus are pretty small. Could it? Possibly, yeah.
So it's like people trying to get to the president, but like.
Yeah.
Okay.
Could it happen? But yeah.
It could happen, but it's kind of hard.
Right. Yeah.
So see, you know how you're talking about another density example?
Yes.
I kind of forget things a lot, so I'm thinking that like it's where I've been.
Yes.
So that you can like find those things, but the things I forget is that.
Okay. The places that you're more likely to be equate to lower energy, at least from an electron standpoint. I'm not sure if I have a good analogy for how that relates to you, right? But
If Hallie was here,
so Hallie, All right, let's think about it this way. If energy is the ability to do stuff, right? Your liking of doing stuff leads you to those places, right? Your liking of swimming leads you to the rec center. Does that make sense? Your liking of your bed leads you home.
So that it's the energy.
Okay, it's the reason that we just feel lower energy first. Missy, go ahead.
Okay, so this was kind of like back with what they were talking about the breaking.
Sure.
So you know how you said that they don't go like on the sidewalk?
Not necessarily
so-
all the time.
So I get that and everything, but what if, like I think I asked this yesterday, I still remember the answer. What if it was in the little figure 8, but it was in the circle too?
Like here?
Yeah. So what L would that be?
Remember that we're trying to, I'd have to tell you. Like, I couldn't just give you this picture and say, hey, where is it? Okay? I'd have to say, this is the location of an electron in the second, in a 2p orbital. What is its set of quantum number? And it's exactly these quantum numbers here. Okay, even though I didn't draw it like there. You know what I'm saying?
For that one, technically, like, if you did give that to us, you would give us the L.
Right. I would tell you it's in a p orbital and make you give me the L.
Exactly.
Okay.
So then that's
That's a Tuesday question. Please go ahead.
Those guys are following that path, right?
They don't follow this path. That's not what we're saying. Okay? That's not how they move. That's just like the edge of the area that they're contained in. But it's not even really a hard edge. It's just sort of a general edge.
Recording us?
Yeah.
Awesome!
Does it record in basic? My kids are
No. Because this discussion, right? There's people talking all over the place.
Oh, no.
And you, like, okay, so, Sadie, we spent an hour and a half doing this yesterday, right? But you still have this many questions. Sometimes we gotta listen to it again, Totally up to you, but it's there for you, okay?
Because when you see that video of like the atom, you'll see like the electrons.
Yeah, that's not how it goes.
See?
Okay. It's not what it's like in real life.
Do you think if I watched the video, I would understand what?
It couldn't hurt, so.
Actually, it could hurt.
No.
Only
All right, are we here? Are we good?
Yeah.
Okay.
What's that?
Let's go here. I think you'll find that the stuff that we want to do today is, based on our discussion from the past couple of days, a lot easier and much easier to figure out. Okay, so, where do these electrons go?
everywhere.
As we've discussed, there's one real idea that governs all of this. And what is that idea that governs why and how things happen?
It's not.
Energy. Energy is the ability to do stuff, and that's going to be the case here as well. So that one energy term that we start off with is called the off-bow principle. That says orbitals are filled from lowest energy to highest energy. Because in nature, we see things tending towards a lower energy state. Orbitals that are closer to the nucleus contain lower energy. And Hallie, we talked about that before, right? That, you fall from the top to the bottom, you're losing energy. Closer to the nucleus equates to lower energy. So orbitals that are closer to the nucleus get filled up first. It has less ability to do stuff. Like in this case, the doing stuff is like giving off light. Right. If it's down low, it just doesn't have very much ability to give off light because it can't really fall anywhere. Okay? And even if it only jumps up like one orbital and falls back down, it can give off a little bit of light, but not very much. So its ability to do stuff just isn't very great. Carter, go ahead.
what like orbitals are filled.
Okay. Hold on 1 second to that. All right. Next on your sheet, there are these two charts. I'm going to focus on this chart because I think it's easier to read. They both tell you the same thing, but I think this one's easier to read. So, if you take a look, what's written on the left-hand edge of that chart?
Increased energy of electrons.
Increasing energy of electrons in orbitals. Which means, where are we going to start on this chart?
Bottom.
On the bottom. So I just put the screen shade up. And I'm going to go here and I'm going to lift this screen shade. What's the first orbital that I run into? 1s.
So that's
Okay.
it.
Okay. It's a circle because, Missy, what kind of an orbital is it?
It's like the L0.
Yes, it's an s sublevel, right? It's an s orbital, so it's a circle. Okay? With that being said, let's go here.
Wait, is n ever 0?
No.
Except for in the nucleus.
I guess n equals 0 probably the nucleus, but that's... Alright, orbital diagrams. Orbital diagrams show the distribution of electrons within orbitals. Isn't that kind of what we were doing yesterday with these pictures? We were showing like that blue picture that had the s and the two p's and the d orbital. I was showing you where electrons were, right? But that gets pretty confusing. Orbital diagrams are meant to show you are meant to show you where electrons are in a more straightforward way. Okay? So let's talk about the very first element, right? Let's talk about hydrogen. So, hydrogen. We need to figure out how many electrons. It's at the bottom of the first page. Okay, so how many electrons does hydrogen have?
Uno.
1. And we know that because
It only has one proton.
it only has 1 proton. And we know that because
Atomic number.
its atomic number is 1. We get its atomic number from
Periodic table.
periodic table. That's what it is. We get it from the periodic table. So, for hydrogen, we have to place 1 electron. Okay?
Actually, well, it would have been
So, we go back to our chart. What did we say the lowest energy orbital is that we can find? 1s. So we start off and we draw a line. And we label that line 1s. That's representing the 1s orbital. So you have
just yes.
remember, that's telling us the shape, right? So it's because it's a 1s orbital, what shape is it? A spherical, right? See, that's the red level that we drew like yesterday. Does that make sense?
Yeah.
That's this. Okay? But now, instead of doing this, we just do this. Okay? Then, within that 1s orbital, how many electrons are we going to find? Just 1, because how many electrons does hydrogen have? 1. We use an arrow to represent an electron. So, I draw my arrow like this. Do you have to draw it with only one pointy side? No, you can draw it with 2 pointy sides if you want to. Totally up to you. Okay? But that's going to be what the orbital diagram for hydrogen looks like. Is this telling you the same information as this picture? Technically, yeah. But do I have to go through all of this rigmarole?
What?
Do I have to go through all this nonsense?
No.
No. But because of what we did the past couple days, you now know that if I say something is in a 1s orbital, you know what shape that orbital is, you know where it is in relation to the nucleus, etc., etc., etc. Does that make sense? It's close to the nucleus because it's a 1. Okay? The arrow represents the 1 electron. Okay? So, Leanna, let's do this. The next one that we get to is helium, right? Okay? Which is the top of the second page. Helium, atomic number 2, that means it has 2 electrons. So we draw a line. Oh, not 2. Sorry about that.
So
Hold on. Okay. What's the first orbital that we want to cross again? 1s. How many electrons can each orbital hold? 2. So I start off and I draw an arrow in there to represent 1 electron. Okay. Now I draw another arrow, but Julia, okay, we're going to draw this one facing downward.
Because they both can be upward. They go like, ooh.
Right?
That's
This gets into yesterday's discussion. No, because Sadie, remember yesterday, our last part of our discussion was that spin quantum number. And if we had those two electrons that were in the same orbital, we called one plus 1/2 and one minus 1/2. All we're doing here with this is that same thing. We're distinguishing one electron from the other. This picture is telling us they're in exactly the same orbital. Now we have to distinguish one from the other.
But what if there's another electron on it? What would you like?
You mean something like lithium? Okay. So lithium, atomic number 3. It has 3 electrons. Okay. So say we go to our sheet, right? And the first orbital we run across is 1s, right? Okay. So 1 electron here, 2 electrons here. But how many electrons do we have to fill? 3. So we go back to our chart, right? Lift up the shade a little farther, and what's the next orbital that we run into? 2s. So I draw another line, and I label that one 2s. And that's only going to have 1 arrow in it. Missy, go ahead.
So would 2s represent like the value?
Yes. This value, right? Okay. So Missy, just to go with yesterday, okay? For this electron right here, okay? Based on just this picture, I can figure out that its n value is equal to 2. What's its L value going to be?
2. Yeah. But why? What's happening on the little finger?
S orbitals, regardless of what level they're in, S orbitals always get an L value equal to 0.
I thought that you could. So the 1s would be n1.
Actually, here, let me do this. Just to keep my coloring scheme proper, right? This is n equals 1, and L equals 0.
Okay, so like that saying like 1s with the 2 arrows is saying that's like the first ring, and then
Right.
the second ring would be n2, and it's just the first part. You don't have to go
Yes. Let's go
What
ahead.
if you have something like uranium?
Okay, so as we keep going with this, okay, so after we fill up this one, where do we go next? Okay, then, okay, now it gets a little weird next because then, so we're gonna get to all this. Hopefully Monday. Okay. So we're gonna get to this. That's where we're headed. All right. Sadie, go ahead.
But since like earlier you had this state like there's 2 electrons on the same sub level. What
Right.
if you wanna like you did it with the up down and like up, 1 arrow up and 1 arrow down, like how do you make the other one?
Let's continue this discussion on Monday. Okay? Yes. All right. So I will give you the quiz, and if you go back to listen to this recording, okay, I'll say it. Do the front page of the quiz, not the back page of the quiz.
Got it.
So there's some evidence that I told you. Okay? I will have this video posted by the time I leave school today.
Which one's the quiz?
What? You can try. It's just we haven't really covered that yet.
Okay.